Good afternoon, everyone. Today's class, we are going to be doing a quick review of what we covered last class, armature reaction, and then we are going to jump into seeing how the motor actually operates, and we'll try to design some controller. Before we come to class, before we meet next week, I would recommend that you brush up on your linear control system course. You should be familiar with what Nyquist plots are, what Nyquist stability criterion is, right? And how to do Bode plot and all of those. So if you're not familiar with those, just brush up and make yourself familiar with it. Because next week we'll be looking at designing a PA controller, and for that we'll require knowledge on the phase margin, gain margin of the system, and all of those, right? So if you're not familiar with any of the terms, just take a control system textbook and read up. It's a pretty simple topic. I will do a quick review, 10-15 minutes review, but it won't be deep enough to cover the full subject matter. If you haven't taken a control system course, please meet me during the TARs. We can go over it. It's going to take quite a bit of time to cover the topic. Okay, so last class, we were looking at the major problem with DC motor. So initially when we derived our equations for torque and current and the operation of DC motor, it was for this idealized motor model where we have our rotor, we have our magnets on the stator, and the magnetic field is purely due to the stator magnets alone. There was no magnetic field due to the rotor windings. And even in that case, we saw that there is problems with commutation where at this angle, so in this particular theoretical case, at the angle 90 degree, the coil, whichever is there at the center point, those are going to have zero EMF across them. But we saw that even if the EMF is zero, the current is not zero at that time. Right? Because it's an inductive coil, there's going to be some amount of current still flowing into it because the current is phase lagging the voltage. So even if the voltage goes to zero, there's going to be some amount of current, but at least the EMF is zero in the ideal case. But in a practical motor, we need to analyze the magnetic field due to the armature windings as well. We cannot just look at the magnetic fields of the magnets alone. And this starts to distort the magnetic field in the air gap as well as in the rotor core. Right? Previously, which was perpendicular and going into the rotor and then going straight lines from the north pole to the south pole inside the rotor, that is no longer the case because in addition to this magnetic field, there is also a magnetic field due to the rotor conductors, which you can figure out by just curling your hands around, right? It's a much more complicated picture than what I've drawn a simple diagram here, because these conductors each have their own magnetic field and they interact with one another. And if there is no saturation, you can use superposition. If it saturates, you cannot use superposition to figure out the magnetic field. In typical case, you would use some kind of analytical, some kind of numerical software to figure out what the pattern looks like. But just to get an idea of what's happening on this diagram here that I drew last class. So we can look at 4 different points and see what the magnetic field due to the magnets are and what is the magnetic field due to the current carrying conductors are. Right? And I already mentioned that the magnetic field is always perpendicular to the iron core from the external magnet. Magnetic field due to the current carrying coil needn't be perpendicular. Right? That's quite easy to visualize. So if you have a current carrying conductor, and let's say I shield it with some kind of metallic structure, there is going to be magnetic field inside this, which is tangential. Right? So it is only applicable for external magnetic fields that are not due to current carrying conductors that the magnetic field will terminate perpendicular, because when we drew this loop and we said integral h dot dl equal to 0 around this particular loop, and we said this value is 0 because the length is very close to 0 and inside the high h is 0, that means outside h must be equal to, so h outside times the length plus h inside times the length must be 0. If this term is 0, then this term has to be 0. But when we have a current carrying conductor, that no longer is the case. Right? Even if the H field inside the iron is 0, externally there can be a H field because it has to satisfy the Ni term. All right. So whenever we do this perpendicular concept, that is only for magnetic field that is not due to the current carrying conductor within the iron material itself. Right. So we are looking at 4 different points that I've drawn here. So we are looking at the magnetic field due to the magnet, which is drawn in black, and then magnetic field due to the current carrying conductor on the rotor, which is drawn in purple. So on the red portion, where I've highlighted here, the B field due to the current carrying conductors in this direction, and the B field due to the magnets are in the perpendicular direction. So the sum of it is going to be pulled down. So whatever the magnetic field is, there is a magnetic field in the counter direction due to the current carrying conductor, which is effectively pulling the net magnetic field downwards. So that's what we are seeing here. On this top portion, we are seeing whatever the magnetic field coming from the magnet due to the magnetic field of these current carrying conductors, the net effect is the vector sum of those two, which is pulling them downwards. And then if you look at this case on the bottom here, again, we have magnetic field, which is going into the rotor, and we have magnetic field due to the current carrying conductor, which is downwards, which is effectively pulling it downwards. So what would have been if it was only the magnet and no current on the rotor, the magnetic field line would have gone like this. But now because of this current carrying conductor having a component downwards, it's pulling the magnetic field downwards. And you can do this again for this spot. You have a magnetic field due to the current carrying conductor going in the upward direction due to the magnet in this direction, so that it ends up pulling it a little bit upwards on the top, right? So this is what the effective magnetic field would look like when you have a current flowing in the rotor. In addition to the external magnetic field that's created, there is a magnetic field due to the armature winding, and the net magnetic field is going to look like this, all right? So this is the sum of it. So Bm, this is Ba, so this is Bm plus Ba, right? Vector addition. So these are all vectors, so it's not just a simple sum of the magnitudes, right? Everybody clear up to this part? Okay. So previously when we saw the point where the loop is perpendicular to the magnetic field, right? That is where the EMF is minimum. Where the flux is maximum is when the EMF is minimum. And we wanted that to be at 0. But now because of this twisting of the magnetic field due to the armature current, right, are called armature reaction, the magnetic axis, so this is the geometric neutral axis, this is the magnetic neutral axis. Previously, the magnetic neutral axis was along the geometric neutral axis. Now the magnetic neutral axis has shifted, right? So the coil here is the one that's perpendicular to the magnetic field. So this is where the magnetic field is perpendicular, no longer at this point. So this point, if you look at it, the magnetic field has some angle. So as the coil moves around 90 degrees, there's going to be a d phi by dt, because phi is the perpendicular component of magnetic field to the coil, right? So the flux, as this angle changes, the amount of flux B field that's perpendicular to the coil changes. But around this point, it is completely perpendicular. So slight variation in and around it would not lead to that much increase in the current, because phi is not varying too much around that point. So this is where the EMF will end up being 0. So what is going to be the problem because of this? What is the issue? Because of the shift in the magnetic neutral axis because of the armature reaction. Any problem? Yep.
If the brushes are positioned vertically based on that picture, then EMF won't be 0 when it commutates.
Perfect. So previously our brushes were right here. Right? Because this is where we expected the EMF to be 0. But unfortunately now our magnetic axis has shifted, but our brushes are still here. So our EMF is not going to be 0 at this point. There is going to be some non-zero EMF here. So at alpha equal to 90 degree, EMF across the coil is going to be some non-zero value. And this in turn is going to delay our commutation, because it's going to source the current through the coil that's being shorted, the coil that's commuting, right? So when we had a diagram for a commutating coil, if you remember, we had this kind of. So we had a brush which was shorting this commutating coil. Now this is not just a inductor coil alone anymore, because there is a EMF across it. So it's effectively an inductor coil in series with some voltage source. So we are ending up sourcing current through that coil. So it's going to delay the time it takes for the current to come down to 0. So by the time this brush moves past this coil and breaks complete contact with those conductors, the current wouldn't have gone to 0, and which then leads to arcing and sparking. I posted a video on Canvas for that. You can take a look at the video where it will clearly show the DC motor starts to arc. So the obvious solution for this is to shift the brush. So this was one of the solutions that we saw, where we can just simply shift the brush and we can call it a day. Then the EMF will be 0 at this point, and then we are no longer shorting an voltage source across an inductor. So there's nothing charging up the inductor. At least the current would not be as worse as it was before. There is still the part where the current in the inductor is delayed. That is not addressed by this shifting of the brushes, but at least we can address the fact that there is no additional EMF contributing to the current being delayed further, right? So this has its own problems. What are the problems with shifting the brushes?
If there isn't like current going through the core, then you are in the same situation, just reversed.
Perfect. So if we don't have any current in this conductor, the magnetic neutral axis would align with the geometric neutral axis, which was this ideal case that we saw, where the rotor current carrying conductors are ignored, right? So, and if the current is very small, it will be very close to the geometric neutral axis. If the current is very large, this magnetic neutral axis will be further out. So as the current increases, it's going to go farther out. As the current reduces, it's going to go closer to the geometric neutral axis. So this axis keeps shifting depending on the current you're working with. So if you have a fixed current, if you typically you would use this kind of arrangement in when you have a traction, like in old trains and stuff. Nowadays, nobody uses DC motor, at least for new projects. But in the old systems where they did have to use it, you would typically shift this brush in applications where the current would more or less be a constant for the most part. There would be some transitions during initialization and during stopping or whatever. But for the most part, it'll run in the same current. In those cases, you can do this kind of arrangement and get away with it, right? What are the other problems that we end up with when we shift the brushes? There was one more problem that we saw due to shifting of brushes. It was a little bit of a more complicated problem. Anybody? Right? So there would be a demagnetization effect that comes from shifting of the brushes. So before we jump into the second problem, let's just quickly look at what the MMR, the magnetic field in the air gap would look like for due to the magnets alone and due to the current carrying conductors alone. Right? So due to the magnets alone, this is pretty straightforward. In the class last time I did stator to rotor as positive, rotor to stator as negative, which had because of which I have to change my angle to this side. So now I'm just going to keep the angle at a conventional starting point at x equal to 0 and change the convention that rotor to stator is positive instead, right? So from here to here, 0 to 90 degree, the field lines are going from rotor to stator. So we have positive. From 90 to 270 degree, it's going from the stator to the rotor. So we have negative. And then again from the rotor to the stator, from 270 to 360. And that is the black line, which is BMS due to the magnet alone. So this is the magnetic field due to the magnet. And to find the magnetic field due to the current carrying conductor, we use the So to find the magnetic field due to a current carrying conductor, we used our formula that if you go around the loop, integrate the H field, it must be equal to Ni. So for the first loop that I have, if I do integral H.dl, I have H1 Lg, where Lg is the length of the air gap, and then H2 Lg, H1 Lg, and here again H1 Lg equal to 0. So H1 over 0, and so on and so forth. If I take a bigger loop, it ends up coming out to be H2 equal to 2 times the current, because there are two current carrying conductors, and then 1 Lg, we end up with 2 Lg, and then H3 was again 4 current carrying conductors divided by 2 Lg. So as we have more and more number of conductors, this increases linearly. So in reality, this should have been like a step diagram, but for simplicity, I've just drawn it as a uniform. So in reality, this would be kind of jagged steps. But if you have sufficiently large number of conductors, this becomes more and more smooth, reducing the amount of harmonics that you have in the waveform that is drawn there. Okay, so before we jump into analyzing the second waveform, I made a very big assumption here, which I was supposed to ask last class, but I forgot. Anybody tell me what was the assumption when I solved this equation? Well, let me put it a different way. Let's say I take a loop like this instead. Right? If I go down and integrate the H field, what is the value going to be? 0. So let's say this is some HA, HALG plus HALG equal to 0. That tells me HA is 0, but I just calculated the H there. Right? H3 was the H when I considered a different loop. When I considered the red loop, this one, and I did the calculation, I got H3 as 4i divided by 2Lg. But if I consider the black loop and I do the calculation, I get H at the same location as 0. Which of the two values are wrong? One of them is definitely wrong. Any guesses? Definitely the one at the bottom is not wrong because I drew the diagram there. I don't want to erase it and change the diagram. But what is the mistake in this drawing that I've done compared to this loop? What was the assumption that I made here? There is no reason for H1 on the top and H1 on the bottom to be the same. Right? So when I draw a loop, and I draw a random loop like this, I can't assume it will be H here and the same H will be here. Right? There is no reason for HA to be equal to HB. That is not a requirement at all. When will it be true though? If I choose it in such a way that the loop is symmetric, right? If I choose it, the way I chose this loop was such that on the top, there are exactly the same number of conductors carrying current in the same direction as in the bottom, right? So just due to pure symmetry, whatever H value is here is going to be the H value that's going to be here, right? But if I choose a loop like this, the number of conductors carrying current distribution here is completely different from the number of current carrying conductor distribution here. Here there is one conductor taking current coming out. Here there are three conductors taking current coming out. Here there are three conductors taking current going in. Here there is only one conductor taking current going in. So there is no reason that the H field on this side should be equal to the H field on this side. So when I drew this particular loop, the equation should have been HA here, HB here, and this should have been HALG plus HBLG equal to 0. I have one equation, two variables, non-solvable. Right? So what I would then need to do is take another loop here, take another loop here, take another loop here, take loops all across this, and I'll get n number of variables with n number of equations, and I can invert it and solve it using linear algebra. Right? But to make it simpler, just because of a symmetry of our motor, if I draw the loop in such a way that it's exactly symmetric so that it encloses equal number of conductors on the top and the bottom, then I can assume H here and H here are going to be the same just because of symmetry. Right? So that's what it comes.
Why are the signs not different?
Why are the signs not what?
Different?
Oh, going from this side to this side. So when we draw a loop like this, right? So we are integrating H across LG length here, LG length here, LG length here,
Okay.
LG length here.
The
Right, so-
LG is minus.
This HG would be in such a way. So if you look at the HG, so let's say the 0 degree, let me draw for this side because that's the one I've drawn on the left hand. So if you look at this at angle alpha equal to 0, so this would be this direction, right? The top one, if you look at it at angle alpha equal to 0, the one going for alpha positive is the positive edge, the one going negative is the negative edge. Right? So the way I've drawn, so the H will come here in such a way that let me say this is some Hx, and this I draw it in the same direction, same direction as this and call it Hy. And if this is equal to HA, this would end up coming out to be negative HA. Right? Instead of putting the negative HA, I'm just flipping the direction and drawing it like this. So that it ends up being the same positive HA. And in my equation, I can just put HALG plus HALG. Okay? Yeah, so the H going on this direction would be the negative of H coming out on this direction. So that's what I've drawn in the MMF, the flux diagram, the B field diagram for the armature current, right? So here, you look at this, this goes negative on the lower angles, positive on the higher angles, right? Any other questions? Okay. So this concept, again, we'll revisit this when we go to AC motors, where again, we want to figure out the H field at the air gap and show the rotating H field of an AC motor. And I'll come back and ask the same question. So all of you, I hope you'll give me an answer at that point, okay? So we'll always choose it in a symmetric way so that we can simplify a calculation, but it's not a requirement though. You can choose any loop, set a number of loops and solve it. If you choose it symmetric, just one equation will give you one solution right away. Okay. So let's come back to our model here. So this is what we have. In a practical motor, what we'll do is we won't have the magnet do a full coverage of 180 degree. We will rather cut it short so that the pitch of the magnet is lower than 180 degree, typically around 120 degree pitch, as I showed you last class, or even the motor that we have in our labs. Right? What was the purpose of doing this? There are two things that we are trying to achieve by doing that. Yep.
Saliency,
What was it?
getting saliency.
Yep. So we are increasing the saliency. So this is called saliency. So this is non-salient. B versus B field in the air gap for a non-salient motor. This is what it will look like for a salient pole motor. So saliency, just the term saliency means that the magnetic field has multiple pathways which have different reluctances. So that if for the current carrying conductor here, the magnetic field has very tiny air gap through which it has to cross through and complete the B field pathway. But for a conductor, let's say here, it has to have a much larger pathway through the air gap, which has much larger reluctance for it, right? So that difference in the reluctance is basically called saliency. And we will use this again when we go to AC motors, for motors like interior permanent magnet, where we'll intentionally create a saliency to produce some additional torques in the motor. So here we have created the saliency. What is the purpose of creating the saliency though? That concept is called saliency. But what do we get by creating the saliency? What are we trying to achieve? Why do we want the reluctance of the conductors on the top here to be much higher than the reluctance of the conductors at this point? Anybody? So when we didn't have that saliency, the problem was our magnetic field due to the current carrying conductor would have looked like this, right? We had some current, we had our H value calculated there, and from the H you can get B, which is just mu naught times H, since we are looking at the air gap. So this is what it would have looked like. And then our net magnetic field would have then be further shifted out from our. This is what our net sum of the dotted red plus the black line would have pushed it way farther out. So our magnetic neutral axis would have been way farther out if we didn't have the saliency. But the minute we add that saliency, around that 90-degree point, the magnetic field due to the armature conductors starts to collapse because you have increased the Lg in the denominator, right? Because previously the Lg was just the distance between the magnet and the rotor. Lg was just this distance. Now, if you look at this, Lg is significantly larger. And just by doing the change, we have reduced the effect of the magnetic field at the 90-degree angle due to the current carrying conductor. That means our magnetic neutral axis, we have been able to shift it just a little bit closer than it was before, right? So where the EMF goes to zero is now very close to where the geometric neutral axis just by introducing the saliency. What is the other advantage we get? Is 90-degree the only point at which the commutator shorts the brushes short the two commutator? You've all drawn the diagram, right, for the homework problem 2 and 3. Was it only at 90-degree where the brushes short the commutator or no? So it starts to short at an angle even before 90-degree, right? The brush has some amount of thickness to it. So it is not only at 90-degree we want the B field to be as close to zero as possible at 90-degree. But even before that, if we can somehow reduce the B field in the air gap, that means we can reduce the EMF significantly at that point. So previously, so let's say this is our ideal B field, then our EMF would have looked like this. So our EMF would have looked like this. It would have had a tiny dip at that 90-degree, and then it would have looked like this again in our DC, the coil that we have. Now, because of this saliency that we have introduced, the EMF would look like this. Right? It would significantly start to drop at the point where it's starting to, even before it goes to the 90-degree angle. And that is quite critical because there is some amount of shorting happening even before the 90-degree angle. So if we can reduce the EMF, we can reduce the amount of current that flows in the brushes, thereby increasing the lifetime of the brushes and also not delaying the commutation too much, right? So the saliency has two advantages: getting the trapezoidal nature of the BM, right? To get this trapezoidal nature and to reduce the value of BA at the peak. So both of these are added values so that they will shift, make the angle delay between the magnetic neutral axis and the geometric neutral axis as close to zero as possible, right? Everybody clear so far?
I'm still a bit confused about the BM, like completely flipping like that for the, I guess I'm just confused about the rotor to stator convention.
or this one.
Yeah,
Perfectly slip
like
this.
what exactly is the point or like line where you define like the
So
rotor
if
and
the field lines go from the stator to the rotor, I'm going to use the convention negative.
okay,
If the field lines go from the rotor to the stator, I'm going to use the convention positive. So
but is it like the entire surface of the rotor and stator?
no, that would be the flux. I'm
Okay.
talking about the B field.
Okay,
B field at every single point. Right? If the vector direction of the B field, so if I have my north, let's just take a planar field. Let's not worry about the fact that these are not 90-degree, which it will be. Just for simplicity, let me draw them as straight lines. Okay. So if you look at this surface, so this is the stator, this is the rotor. Everywhere on the left-hand side, the field lines are coming from the stator to the rotor. And everywhere on the right-hand side, right after 90 degree, it's going from the rotor to the stator. So according to a convention, that is basically saying that here it's completely positive, here it's completely negative. Okay. So you can think of it as encapsulated by two magnets, two arc magnets, such that this side is fully north and this side is suddenly gonna make a step change to south. Okay. So that's what this flip essentially means. In reality, there would not, even if you had this kind of magnet, right, where you had a perfect north here, perfect south here, it would still not make that vertical change, because the minute this north is getting closer to the south, this field would weaken this out. Right? There would be some amount of weakening of the north pole around these edges, and there would be some amount of weakening of the north and south pole around these two corners. So it would always be more or less trapezoidal, but we want to make it significantly trapezoidal by adding the tangent. Right? Any other questions? Okay. So we looked at the magnetic field due to the current carrying conductors here, and we drew these field lines, and we saw that for the conductors on the top, they create a H field and the B field in such a way that they are opposite to the magnetic field coming from the magnet. And on the bottom, it is going to create magnetic fields that are in the same direction as the external fields of the magnets. Right? So one half of the pole face, our magnetic field is getting weakened. Other half of the pole face, our magnetic field is getting strengthened. What is this effect called? So this magnetic field that we have here, is this cross magnetization or direct magnetization? You remember I gave you two terms in last class. When is it called cross magnetization? When is it called direct magnetization? Is this magnetic field in the direction of the external magnetic field, or is it perpendicular due to the armature current? Compared to the drawing on the top, what is the direction of the field lines inside the rotor core? Perpendicular. Right? Our external field is in this direction, our B field inside the rotor is in perpendicular direction. So this is called the cross magnetization field. So it's called a cross magnetization field. And if we have components in the direct axis, then we'll call it direct magnetization field, which we'll look at in a minute. So the cross magnetizing field causes demagnetization due to cross magnetizing armature reaction. So why am I calling it demagnetization? In fact, it's actually increasing the magnetic field in half the side while reducing it in the other half. Right? So in effect, it actually looks as if it doesn't do much either way. So half the pole face it weakens, other half the pole face it strengthens it. But why do I still call it demagnetization effect? There was one assumption that I made when I summed these two waveforms together. Right? When I took the black waveform and summed it up with the red waveform, can I do that to magnetic field? Can I just simply sum them up? When is that summation all up? When can you do superposition of magnetic fields?
When they're parallel.
When they are parallel, no. Even if they are not parallel, I can do vector summation. Right? That's a very good answer though. I can only do magnitude summation and call it the vector summation if they are parallel. That's absolutely true. But yep, exactly.
Same direction.
They are in the same direction. That would be the same as what you said, right? Parallel. When does superposition fail?
Non-linear.
It's non-linear. Perfect. So we can only add things together if they are linear system. When we have these magnetic fields, as long as the core hasn't saturated, right? So if I have a BH curve like this, let's say I apply 1 ampere and the B field is 0.5 Tesla. And if I apply 2 ampere turn per meter, let's say it goes to 1 Tesla. But then if I apply 3 times, it won't go to, unfortunately, 1.5 Tesla, but it will go to 1.3 Tesla. Right? So this is what saturation effectively is. You can add more current to it, but it does not linearly increase. Once we enter the saturation region, we cannot directly just sum these waveforms together. So the net magnetic field is just not the sum of 2 magnetic fields alone. For instance, let's say you have an iron core and it has gone into full saturation. Let's say you push 2.3 Tesla. No matter what powerful magnet from the world you can bring in or you put an extremely powerful coil, the magnetic field in the iron core is not going to increase past 2.3 Tesla or 2.5 Tesla. You're going to require enormous amounts of currents to push it any further, right? It doesn't operate linearly at that point. So we cannot just simply add these 2 values together. When we add them up, so the amount it falls versus the amount it raised would not be the same. So when we sum those 2 values together, it is not going to give the same as when it was subtracted out. Right? So this area is not going to be the same as this area. In fact, when we have this phenomena, the amount we gain due to the magnetization factor, right? So these field lines are increasing the magnetic field, but the amount increasing the magnetic field is not proportional to the amount they demagnetize the magnetic field because of the saturation. Because of saturation, this does not increase as much as this has fallen. So what that in effect is, over the total surface of the magnet, you have effectively reduced the magnetic field by a tiny amount of portion. Right? So that's why we call it demagnetizing effect of the cross-magnetizing field. If it was a linear system, there would be no magnetization, there would be no demagnetization in the net. Because half the side is magnetized, half the side is more demagnetized, so you don't gain anything much. But in reality, due to saturation, some portion of it loses more magnetic field compared to the other portion, which is gaining the magnetic field. Okay, what is the problem because of this? What would happen in the motor because of the reduced magnetic field? What do we lose out on? The torque, right? So this expression that Ke we derived last class, that was Ke which is equal to Kt, Nc divided by 2 times R times L times B of the magnet. Right? This B value is starting to reduce. So if this B value started to reduce, the Kt value reduces. So for a given amount of current, the amount of torque that the motor can produce starts to fall down. That means you would need to push more current to get the same amount of torque. And the problem with pushing more current is you start to have more losses as well because of the Ra component. Right? So this becomes the problem. You start to have loss of efficiency because of this demagnetizing effect. Okay? Anybody has any questions so far? Okay. So now let's look at what happens due to the shifting of the brushes. So let's say I put my brush here now. So conductors on the left of the brush have current in one direction, conductors on the right of the brush have current in the other direction. And now again we can draw the magnetic field. I can split it now into these conductors and then these conductors and then these group of conductors and then these group of conductors. Right? And now I can draw the magnetic field lines for each of those. So we have field lines like this, field lines like this, Lines like this, and then field lines like these, right? So these three set of conductors and these three set of conductors are still the same as the previous case, which are just creating cross magnetization component within the core, right? So within the core, they're only creating cross magnetic component. But due to the shifted brushes, we now have components which are in the direct axis as well, right? So our external magnetic field is coming like this, but due to our shifted brushes, a portion of the conductor are creating magnetic field in the opposite direction to the external magnet, and this in turn demagnetizes the magnet directly. So here, this demagnetization was due to the nonlinear saturation effect. In this case, the demagnetization is total across all the full pole phase. So this is demagnetization due to direct magnetization of armature reaction. And both of these demagnetization have their own problems. As we saw last class, they'll make the motor unstable. So because as the load increases, the speed of the system would come down, speed comes down, EMF has to come down, EMF comes down, the current increases, right? If the EMF reduces, V minus E increases, that means the current increases. If the current increases, there is more demagnetizing field, which will then reduce the torque even further. And then as the torque reduces, the speed reduces, the EMF reduces, the current increases. It's an infinite cycle to the point where the motor will come to a stop. Right? So this usually happens when the core is saturated, and no matter how much more current you push in, this magnetic field is not increasing. So there is no additional torque produced due to this, but this is constantly demagnetizing it as more and more current increases. So the torque starts to reduce and it comes to a full stop. Right? So these are the problems that we have with our DC motor. So we have our demagnetization due to cross magnetizing field, demagnetization due to direct magnetization field, and then the delaying in the commutation because of our armature reaction, which shifted the magnetic neutral axis, which led to some amount of EMF if we had our brushes here, which in turn causes a lot of problems, delay, which causes arcing in our motor. What are all the methods to solve it? We saw one method is shifting the brushes, right? But shifting the brushes has its own problem, creates the direct demagnetization effect that we just saw. So that is to be avoided as much as possible, especially at very high power motors. Low power motors, it's absolutely fine. Even the lab motor, you'll see the brush is slightly shifted off axis. It's not exactly at 90 degrees. There'll be a tiny offset. That's a very reasonable solution for low power motors because your core does not saturate for low power motors typically. But for high power motors, core does typically saturate at rated current. And once it saturates, you end up with the problem of where even a slightly higher amount of torque could completely stall the motor. And a stalled motor is a very big problem because if the EMF goes to zero, you have a huge amount of voltage across just the resistor, right? There is no LDA by dt, there is no E, there is just V divided by R, and the resistance is like 0.1 ohms or even lower for high power motor. So the current would be way higher than the rated current, and the motor winding will burn out. That's a very big problem. So we can't use the brush shift method for high current motors. So what were the other two methods that we discussed to eliminate armature reaction last class? What were two other solutions? Yep.
Was one like placing electromagnets perpendicularly to the stator magnets?
Perfect. Remember the name? Right? Interpoles. So it's basically a pole placed in between the two other main poles, right? So you have the wire coming out from the brushes of this motor, right? Typically, these are the two wires that come out in the DC motor that we have. So when we have this motor here, so this does not have an interpole, nor does it have a compensation winding, which is the other method. So if you look at this, the brush and the wires are directly coming out from the brushes. But in this case, what will happen is there will be a wire that comes out from here. There will be a protrusion here on which there will be a bunch of windings. And then that is the one that will come out as an external wire when we have an interpole compensation. So this wire comes out and it's wound on this, and then this wire comes out as some positive terminal, let's say, and then the brush would wind on this and then come out as the negative terminal. So whatever current flows in the armature is flowing in this winding as well. So we can operate this in such a way that the magnetic field created due to this is opposite the magnetic field created due to the armature reaction. Oops, sorry, the other way. Right, so what in effect we are doing is reducing the height of this armature reaction. So So with saliency, we already got this. We can reduce this even further. And we can increase this even further. So that it's much closer to zero, and what that will then mean is the sum of this black and this red waveform would now be much closer to our geometric neutral axis. So the delta shift, we are reducing it as much as possible, bringing it even further closer. So we can completely eliminate, if we put sufficient number of turns, we can completely make it go to zero. Therefore, the EMF is zero at the geometric neutral axis as well, so that we don't have to do any brush shifting. We still haven't addressed the problem of LdI by dt. So when the voltage is zero, the current is not yet zero. Ideally, at 90 degrees, we want the current to be zero. How can we address that? Using the interpoles itself, how can we address that?
Compensation winding.
Compensation winding? No. Using the interpole itself. Compensation winding is a completely separate method. Using interpoles, how can we? If you remember, we looked at the case where our EMF, if this is our voltage and our current is phase delayed, right? But if we shift our EMF backwards, then our current is also shifted backward. Let's say this was pi by 2 before. We can make our current go to 0 at pi by 2 by shifting the EMF backwards. And how do we shift the EMF backwards? Why just stop at 0? Why not make this coil generate a negative EMF by making the magnetic field go even further negative? Right? So that the sum of it, this and this waveform, the blue waveform, actually goes to 0 even earlier than 90 degrees. So what in effect is you're putting a coil here, which was previously positive or negative here, but flipping the direction now, making this negative, this positive. So it is creating a voltage that is countering the current that's in the coil, so that you can bring the current down much faster. Do not have to wait past pi by 2, but even before that, you can bring it down to 0. All right, so interpoles will allow you to compensate for not only the effect of armature reaction, not only bring E to 0, but it can also make E go negative so that the current goes to 0. So you can compensate for the LdI by dt effect. Right? Current goes to 0. So both of those can be achieved. So the final method that we saw is our compensation windings, where we have these conductors and we have this pole face. Why not just put a, so this was the case when we had our phase, a shifted neutral axis. For high power motors, you won't shift it at all. You'll definitely want to put it right in the center. And then we basically have conductors on the stator core, which exactly cancel out whatever the field lines are created by the conductors on the rotor. So on the stator pole face itself, so you have some winding which is creating the north pole, and then you have some winding which is creating the south pole. And within this pole face, you put some holes and put some windings in there. So that whatever current is being drawn in the rotor on this side, the opposite direction current is drawn by the conductors on the stator face. So what then happens is whatever field lines this conductor is creating, it's going to be cancelled out by field lines of this conductor. Because again, these are exaggerated air gap. This distance is extremely tiny. For high power motor, 0.2 millimeter or lower is very typical. Right? So this is as if these two conductors are placed extremely close together. So if that is the case, and this is carrying current in one direction, this is carrying current in the opposite direction, the B fields are going to cancel out perfectly. So once we cancel out those B fields, there is no effect of this demagnetization effect, right? So we don't have this direct demagnetization effect caused at all. So compensation winding can address the fact that the magnetic neutral axis is shifted. So we can put sufficient amount of current so that the magnetic neutral axis and the geometric neutral axis are aligned. And we can also compensate for the demagnetization effect. So both of these get eliminated when we use these compensation winding. When we use interpoles, we can again make sure this is aligned, and we can also make sure LdI by dt is eliminated. Interpoles does the other two. So MNA equal to GNA, and then we can eliminate LdI by dt effects by shifting the voltage forward backwards. Interpoles cannot compensate for demagnetization effect because it only creates cross magnetic field because of the way it's positioned. Right? There is nothing it can do to alter the direct magnetic field that's going on. So interpoles cannot address demagnetization. Compensation winding cannot address LdI by dt. right? Because again, it creates only magnetic field in this direction, it cannot interact with the interpoles direction, right? So they do have different applications. So when we have a very high DC for DC motor, you would have both use compensation winding as well as the interpoles, so that you can compensate for both of those. Right? Yep.
Does it still work like even when the motor moves to a different position?
Motor.
Like if it rotated or is it?
Oh yeah, it would, because even if this rotates, right, conductors on the right would be current going in, conductors on the left would be current going out. That's what our mechanical commutator is doing, right? Ensuring that the left half is always, without the commutator, the motor would not be, so that it would be just an expensive pendulum, just rotating back and forth. Any other questions? Okay. So let's get to the topic for today, which is our operation of DC motor. So again, there will be no questions in the exam on this. There will be a couple of questions on the project, but otherwise on the exam, I won't ask anything related to this. So we have our 4 equations there. Let me start out with a very simple case. Let's say I apply a terminal voltage of 10 volts on the motor, and let's assume that the resistance in the motor is negligible. Let's assume the friction in the motor is also very negligible. And let's say I give you the Ke, Kt to be equal to 0.1. What will be the speed of this motor at steady state? What will be the speed of the motor at steady state? So again, by steady state in DC circuit, what do I mean? What does steady state in a DC circuit mean?
No time varying components.
No time varying components. Perfect. So under steady state, this term disappears. This term disappears. I've said there is no friction. This term disappears. I said negligible resistance. That term disappears. So straightforward, our voltage is directly equal to the back EMF. And we know our back EMF is K times omega, right? So if I have 10 volts, V was 10 volts from our above equation, that is same as the back EMF E. And then our omega is just going to be E divided by Ke, which is going to be 10 divided by 0.1. Our motor is going to settle down at 100 radians per second. Okay. Now, if I introduce resistance, is the system still solvable? Let's say I say the resistance is not negligible. There is some resistance. Let me give a value for it. Let's say R is equal to 1 ohm. Do I need to know anything else to be able to solve the system?
Current.
The current. All right, so let's, so we have 10 on the left side equal to E plus R times I. Right, E itself we can replace it as K times omega. I itself we can replace it as tau em by K. Tau em by K. Again, these two terms are 0. Tau em is just equal to tau L. So K times omega plus R divided by K times tau L. Okay, so as long as I give you the load torque, you can still find out what the omega value is going to be. So there's just one more value that I need to give if I start introducing other parameters into this equation. If the load torque is 0, then our speed is going to be exactly same as before. If there is no load torque and there is no friction in the system, there is no need for current to flow in the motor at all at steady state. Right? Because if there is a current flowing in the motor, what is going to happen? There's going to be a torque produced. And if there is a torque produced, it is going to infinitely accelerate the system, right? Which will be problematic. So in our case, given that we don't have the system, we don't have any friction, the solution straightforward, if torque is 0, is going to be that the current is 0. Okay, let me say the inertia term exist, B term exist. All of these exist. Is this system, how many variables, let's say I've given you all these parameters. I've given you J value, I've given you B value, K, KT, L and R. How many of those variables do I need to know to solve the rest of the variables? How many variables are there in those equations? Just look at the equations and what are all the variables. You can start naming the variables. What is it? Can you throw out the names of the variables that we have in those 4 equations? Voltage, thank you. What are the variables?
EMF,
Voltage, EMF, and then current. Okay.
resistance.
Resistance would be a parameter of the motor.
Okay.
It is not something we can control. So inductance again is a parameter of the motor. So the motor parameters would be the resistance, inductance, the inertia, and the friction. So once you're given a motor, those are all determined. Once you're given a motor in the system, there are other things that you can control. What else can you control?
Tau EM.
Tau EM. Right? Anything else? What was it?
Angular speed.
Angular speed. Anything else? Tau L. So if you assume the current to be a variable, tau EM is fixed solidly, right? It's no longer a variable. It's a determined value at that point. Or if you assume tau EM is something that can be controlled, then the current can't be controlled. Right? If you control the electromagnetic torque, then your current can't be controlled. If you control the current, your electromagnetic torque cannot be controlled because they're exactly a scaling factor. They're tightly bound together. Same as this, right? If you have your EMF given, your omega is determined. If you have your omega given, EMF is determined. So these two occur in pairs. So the other two control variables are your voltage and your torque. So in a motor, if I give you what the terminal voltage of the motor is, and if I tell you what the load torque is, there is only one solution for this. It will go and settle down to some particular speed and it will go and settle down to some particular current. Right? So if I'm now letting you control, let's say I give you the value of load torque, which is not under our control. Let's say this is not controlled by us. So this is determined by system. Basically, if you have an elevator, number of people getting in, and so on and so forth. Let's say we don't have control over this variable. So the only variable that we can control is going to be our voltage. Right? Given this, can I control both the EMF? Can I control both the speed and the current in the motor? Let's say I want to get to some particular speed in the motor and I want to get some particular current in the motor. Can I control both of those in this particular situation? No. Okay. So this is an important thing. Like when you have only one control variable, you can only control either the current or the speed in the motor. You cannot control both of them at the same time because these two are independent variables. Right? So if I tell you, if the load torque is determined by something else and you are able to control the voltage, you can create a control loop so that you can control the speed of the motor or you can control the current of the motor. You cannot create any kind of control system such that you can control both the speed and the current at the same time. Right? But let's say you have load torque as well under your control. So if you can control both the voltage and you can control both the load torque, then you can control both the speed and you can control the current. Right? So depending on the number of control variables you have is the number of control elements that you can control. Right? So that has to be matched up. Anybody has any questions? So let's go ahead and try to model this. Let's say we want to build a Simulink model, which will be the homework for next week. I've given the 4 equations in the boxes there. Let's start off with the electrical equation. So typically the voltage of the system is given. Right? Let's say you didn't attend this class today and you just saw the homework, how will you proceed with drawing the Simulink model for it? What would you do next? You have your voltage. What else can we? How do we proceed with drawing the Simulink model for this motor?
Inductors.
Who's it?
Inductors.
inductors. So we are going to use, in Simulink, there are two options. You can either model it using power elements, or you can model it as purely mathematical elements. Right? We want to stick with modeling with mathematical elements, as we'll see in a minute why. We get a lot of advantages. It's exponentially faster to do the simulation when you have mathematical elements. And second thing, when you go to AC motors, the inductance starts to change. It becomes very hard to model things as a variable inductance in power toolboxes. All right, so you want to do it mathematically. So we are going to do purely mathematical operations, addition, multiplications, and that's it. All right, so you either use an adder block, or you use a gain block, or an integral block, or a differential block. So these are the only 4 elements that we are going to be using to build out the whole model. So what do I do next? There are no wrong answers. There are multiple ways you can implement that model. Just give me one method. Let's say there's a control theory course that you're given those equations and you're asked to model it in MATLAB, not using state space. So I'll simplify life too much.
Start with what adds up to voltage.
Perfect. What adds up to voltage? So let's do it the other way around. So we have our EMF coming in. We have our LDI by dt, right? So some d by dt block, and then multiply by some L block, gain block, and the input of this is current. So we have L times I, the whole differential, LDI by dt, and then take the same current, multiply by the resistance, add them up, and this is going to be voltage. That's a very good answer. The only problem is voltage is input to the system. Voltage is something I have given. But through this diagram, you are giving me a voltage which would not match the voltage that I've given, which is not going to give me a solution. So how do I flip the system so that the voltage is the input? How do I restructure it so that the voltage is the input?
You do the inverse process where you subtract off the EMF and you back calculate the current.
Perfect. Back calculate. So there are two methods. So the answer Ben gave is you have the voltage, subtract out the EMF. We don't know what the EMF is. Here again, we don't know what the current is. The voltage is only given value. You subtract out the EMF, and then whatever the rest remains is L di by dt plus Ra, right? So this is one possible solution. Where I'll complete this in a second. Some set of toolboxes must come here so that the output of this is correct. Another way to do this would be if I swap this term around. So if I look at the equation, if I leave EMF on the right hand side and bring everything else to the left hand side, so V minus L di by dt minus Ra is going to be the EMF E. Right? So I want EV to be the input. So both of these are feasible solutions. So let me complete the second method that Ben mentioned. How do I get, so once I have V minus E, how do I get to I? Keep chipping away blocks until take out elements that are easy. So Ben gave a very nice answer. So the equation is V equal to E plus L di by dt plus Ra. So E is a troubling term. Let me subtract that out. What else can I take out of this?
Divide by R. Or
What was it?
you can subtract L di dt.
Subtract L di dt, right? So let me instead subtract out Ra. I'll get to why I'm not subtracting out L di by dt in a second. Right? I've subtracted out Ra. Whatever remains is, if I take V minus E minus Ra, what is remaining? The first equation, what is the only term remaining if I take out all the other three?
LDI.
L di by dt. So if I divide this by L, what is remaining is di by dt. How do I get I? The output of this is di by dt. How do I get I out of it? Integrator. So put an integral block and you get the output. So there are two methods. So we could have either done this or done this. Which one would you prefer? All of you would have done control simulations for your Simulink. Whenever you're given a set of equations, even in state space model or whatever, you always try to set up your equations as an integral form or a differentiable form. Which one would numerical simulations prefer? What was it?
Differentiable.
Why differentiable?
Easily solved.
Listen though. The operation for both is exactly the same. So this, if you take a first order solver, all it's going to do is look at time plus 1 and subtract time minus 1 divided by delta t. That's what a differential operation is. Or I shouldn't say t plus 1, t plus delta t. An integral is pretty straightforward too. So it takes whatever the input is coming, right? So it's going to take the, let's say this is the output. Let's say this is the input. So output at time t plus delta t is equal to output at the previous time instant plus input at the previous time instant times delta t. So either of those operations are pretty straightforward. I prefer this operation or this operation because division is quite complicated operation. Typically, you can do multiplication on a floating point processor in a cycle or two. Addition is a single cycle operation. Division typically takes about 14 cycles of an operation. Right? So it's more expensive to do differentiation compared to an integration in reality. But there is a much bigger problem. Why do we? So we want to avoid differentiation at all costs in numerical simulation. Whenever it doesn't matter which field you are in, if you have a bunch of equations, you would always rewrite the equation so that you end up with an integral and try to avoid this differential as much as possible. What is the issue? Yep.
If delta t is small, it can get really large.
Yep. So typically what we do is when we look at this integral operation, whenever we do numerical simulation, we'll make this delta t as small as possible so that we can get really nice results that closely match with what reality would be. In reality, delta t tends towards 0 in real world, right? But when you do d by dt, if this delta t becomes very small, even if there is tiny mistake in this, the current instance was next instance, the error will get amplified extremely, right? And this error can come from multiple points. Error can come from noise or error can come from rounding errors. So in a numerical simulation, if you had infinite precision available, then you can do this and this both will give the same result. But in reality, there is no infinite precision. Even if you take a floating point process, that's just 64 bits. There's only a certain amount of bits available to represent the fraction part. So at some point, if the fraction is going to get rounded up or rounded down, there's going to be some amount of error created. And if you use a finite amount, a very small amount of delta t, that is going to create a large amount of error in the d by dt operation. And that keeps accumulating every cycle, right? Next operation will get added on to it because it's I plus whatever the previous current was here comes into the picture. So it keeps on accumulating to the point where it will diverge and become unstable. So when you do the homework, try both methods. I haven't asked you to do the differential way of implementing it. I've only done the integral. But try this too. You can never get a delta t that will make it converge for the parameters that I've given you in the system, right? It won't. You'll have to either use a very large delta t, in which case the answer will be complete garbage, but it will converge. Or if you use a very small delta t, it won't converge at all. It will completely diverge out. So there are certain problems where differential is the only solution. You can't rewrite it in a way that it's purely integral because of other constraints. But whenever you can, you would put it in integral form, right? So once we have current, what shall we do next? So this is the way we are going to go. No longer we are going to worry about implementing differential operation. How do we proceed? What will be the problem when we have noise? What happens to d by dt when we have noise? It amplifies it, right? So when you have this kind of signal, differential at these points would just make it spike all over the place. Okay? Noise gets amplified when you have a differential operation. But anyway, so what do we do next? Once we have current?
Use the gain block to get TEM.
Fantastic. Use the KT block to get TEM. Okay, what can we do next? Once we have TEM, you're already seeing the pattern I've done here for the voltage equation. Right? We can repeat the same equation that we have. So whenever you look at the motor equation, look at the electrical system and the mechanical system, they're exactly replica of one another. It is just that the L is replaced by J, R is replaced by B, and then the E is replaced by tau L. So the same thing here. We have electromagnetic torque, subtract out the load torque. Whatever remains, subtract out. What can we subtract out?
Do we know we subtract out d omega?
D omega. Do we know omega?
You can find it.
How?
Integrating the output of that block.
Is it integrating the output or?
Or
Yeah, you're very close. Integral would give me something, but is that all? So we have tau em minus tau L minus b omega is equal to
J times d, so we have to scale it by 1/j.
perfect. So scale it by 1/j and then integrate it. So this would be d omega by dt. And if you integrate it, you end up with omega, close the loop here, right? What else do I need to do? What else do I not know? When I got the current here, I could have closed the loop here, right? Is the model full, complete? Is there anything else that needs to be done, or is the system done, complete?
It's only the E, right? Yeah.
Okay, so once I have the speed times K is going to give me the back EMF, right? So you complete the full model. The voltage will be given, the load torque will be given, and then you implement this model, you can figure out what the current is. So you just put a scope here. And that will give you the current. You put a scope on this. That is going to give you speed omega. Right? Straightforward, simple system. Anybody any questions on how to model this? In MATLAB? Right. So this whole thing right here, I could have instead replaced it with a transfer function. Right, so let me draw it in the form that you might be more comfortable with. Here. And then B here. And somebody tell me if I convert this to transfer function, what this will come out to? This whole thing within the brackets. You don't even have to do g of s divided by 1 plus g of s h of s to figure it out. The answer is much simpler than that. But I'm asking you for the transfer function between omega and tau em minus tau L. Right? Input is tau em minus tau L, output is omega. The transfer function between omega divided by tau em minus tau L, what will that be? You've already done this in your exams, in your homework.
Is it just JS?
Okay. JS, is that the only term?
How L over S?
Tau L is already here on the denominator. So from the equation there, if I take the Laplace of it, it's tau em of s equal to tau L of s plus sj times omega of s plus b times omega of s. So my question was, what is omega of s divided by tau em of s divided by tau L of s? Okay. So it's just going to be 1 by sj plus b. So this whole thing can be replaced in transfer function form. 1 by sj plus b. Which one would I prefer? Having the integral form or the transfer function form? I assume all of you would have used the transfer function block in MATLAB, right? What is the limitation? The transfer function block?
Stability.
The transfer function exactly, if you look at what this does, it will break it down into this form and solve it for you as an integral equation. Right? Whatever you have here is exactly the same as happening here as well. So if this is unstable, then this is also unstable. Any other problem? In an integral block, there are two values that you can add. Whenever you put this integral, there is an option for you to put a gain for that integral so that these two blocks are mixed together. What is the other option in an integral block in MATLAB? You can set an initial value to it. Right? In a transfer function, you cannot set an initial value. Because the way this, for a first order system, it's straightforward how we'll decompose it. For a higher order system, there are internal states that will be created which you cannot initialize because depending on the complexity of this transfer function, it will create different kind of state space model for it. Right? So the inner variables cannot be initialized. So whenever you want to initialize your current to some value, initialize your speed to some value, you would use it in this form. If you don't anticipate any kind of initialization, you would use it in this form. When would you want to initialize? Why would you want to initialize at all? Right? When I start this motor, the current is going to be zero, the speed is going to be zero. Right? So why do I need to initialize? And if I use a transfer function form, it will assume the state starts at zero. That's all good. What would be the reason for initializing it?
System is not at steady state or hasn't been settled.
Yeah, when we start off, it hasn't settled, right? And it isn't at steady state either. If you flip your answer around here, you have the correct answer. If you want to start a system that's already at steady state and run your simulation, then you would want to initialize it with some value. And the reason you would do that is when you run the simulation, you'll see for a DC motor, at least it runs fast enough. But when we go to AC motors, there'll be a whole bunch of parameters and the calculation takes a lot of time. So typically when you run these systems, you'll design a controller and you'll assume that the motor is already operating at a steady state point. You want to see what happens when you apply a step load change in the torque. You would want to do like 1,000 different iterations of simulations to see, irrespective of how the load torque changes, the system is always stable. Right? In those cases, if you want to start from the time equal to zero, wait for it to settle down, and then do these load changes and then analyze and then repeat this 1,000 times, it's going to take forever. So what you would rather do is you would apply some voltage, theoretically calculate what the steady state conditions are, which is what we just did a few minutes back, right? By making all the differential terms zero, and then initialize those values, integral values to the steady state value. And then you can go through quick iterations of just changing the step load for multiple different values and get the results really quickly, instead of having to wait the whole time for it to come to steady state and then start to apply the values, right? With that, let's call it a day for today. And then next week, we'll look at how to control the system. Because here, depending on what the load torques are, the speed is going to be changing, but we want the speed to remain constant, which we'll do next week. Before you come to class next week, please make sure that you take a look at control system.